the previous section, Mohammed has introduced some special neural network architectures for image data. And now we will do something similar for sequential data, like text, time series data, or speech. And this will lead us to recurrent neural networks and transformer networks. Sequential data can take a variety of different forms. We could have, for example, text data, where we have a sentence or entire paragraph as the input. We could have speech data, where the speech signal of, for example, a sentence spoken is our input. Or we could have a time series, where we have different values over time for example, temperature here. What they all have in common is this time dimension. So they all have discrete time steps that are underlying the data. For a concrete example, let's consider text data, where we have a sentence or part of a sentence as the input, and each word would correspond to a different time step. So we have each word being assigned a time, and therefore also in each time step we have each word corresponding to a vector. So each word is its own input, x0, x1, x2, x3, and so on. So we have a sequence of vectors that is the input to our model in the end. For these different types of data, we can also have different tasks, where one task could be predicting the next time step. That would be for text data, the task of language modeling, where here we would have the start of the sentence neural networks are, and then we want to predict the most likely next word, which would be, for example, awesome. For sequences, we can also have classification tasks, where we process the entire sequence, and then we want to do something with that and classify this sequence. And here, the classification means assigning a sentiment to the sequence. And here, in this example, this would be a positive sentiment. So we classify this as a positive sentence. For sequences, we can also have the type of sequence-to-sequence tasks, where we try to predict an entire sequence based off our input. So here we would have a translation example, where we have an English sentence, neural networks are awesome, as the input, and we want to predict the German translation, which would be neuronale Netze sind großartig. That sequence does not need to be of the same length in this example. So here we would have a very unrestricted task where we predict from one sequence to another. Let's take a look at how we process sequences and first of all text or individual words in neural networks. Here, taking one word as the input, we first need to vectorize it. So that means for each word we look up in our vocabulary what corresponding vector it's assigned to. And each word has, if it's the same word, it needs to have the same vector, and what vector that is learned jointly with the rest of our neural network. So these vectors are then passed into the neural network and processed in the same way as we would with any other vectorized input in the neural network. And then finally, we can predict our output. And if that output is supposed to be another word, then we have a classification task, because each word in our vocabulary, which can be thousands of words, is assigned a different class. And then we just have a classification task of what is the most likely word for our output. Considering this on a more abstract level, we have multiple functions that represent each layer that process the input, which is a word, and generate another word as the output. But how now could we process multiple words that are sequential in time? For this, we apply something that is called recurrent neural networks. This means on each layer, we have these loops that feed the output of this layer back to itself in the next time step. So in the first time step here, we would have neural as our input, and we want to predict the next word. So we just process it feed forward through our network and then have this word networks as our output. That's as far as we know it, but now we go to the next time step. So the input shifts, and now our recurrent connections also come into play. So we not only have the input from our word, but we also have the output of the previous time step in each layer that we can process to get some context from the previous sequence. So we process the sequence one word at a time. And the same is now repeated. And we carry this context throughout the entire sequence. So we move in the sequence forward, and then we activate these recurrent connections that feed back the information through time. And then we can predict the next word in the sequence. And we go on, one word at a time, passing it feed forward through the network, while at the same time in each layer getting this recurrent connection. And with this, we can basically process the entire sequence and predict one word at a time. Now, if we look at this over time, we can also unfold this and look at how each time step connects to another. And this means we have this connections from one time step to another, where each time steps shares the weights with the previous time step. So we always have the same network function, but different inputs, because we have on the input side that is our sequence, different inputs, and we also have different inputs from the context that is handed over time. And this is basically how a recurrent neural network would look like unfolded. So we process this and hand over the context. What we've just seen is a language modeling task where we want to predict from each word the next word in the sequence. And for this, recurrent neural networks are quite useful. However, they could also be used for a sequence classification or prediction task where you predict just a single output for the entire sequence. So we first process the entire sequence with a recurrent neural network, and then the output of our last layer in the last time step is a representation of the entire sequence, or considered as that, and then used for some classification to get our final output, for example, the sentiment of our sentence. Recurrent neural networks, or RNNs, how they are called, can be trained similarly to standard feed-forward networks. That means you would unfold the neural network over time, as we have seen, and treat it as a normal feed-forward neural network, but you would still consider that each time step shares the same network function or same parameters, just with a different input. And in this way you can train them, but recurrent neural networks tend to forget their context when you have a longer sequence. So this is of course a problem, and people address this, and there are versions of recurrent neural networks that don't have this problem that much. For example, the long short-term memory LSTM unit that basically serves as a plug-in replacement for recurrent neural networks, and as a variant of neural networks, recurrent neural networks is quite successful. Another very successful architecture to apply for sequences is called self-attention. Here we again consider the sentence neural networks are cool as our input. And for each time step then we would have a different vector representing one word as our input. And now let's consider the case where we only want to generate the output for the time step neural. For this, in self-attention, we would consider each other time step and also its own time step as a context. And we weight these different contexts to get the output of our layer. For this, we first need to transform our inputs in different ways. For most positions, we just generate a key and a value vector by applying these small layer functions fv and fk to generate a key and a value vector. And these are, of course, shared across time. So the functions are shared across time, but of course they have different inputs. And for the position we want to generate our output for the position of the word neural, we also apply a function fq to get a query vector. And with this query vector, we can now perform our weighing of the inputs, of the contexts. And this is done by comparing our query vector with all the other positions in our sequence. So we take the query vector and just compare it to the key vectors of all the time positions. So for the first time position, we compare it and get a scalar weight out of this. Then we compare it to the key vector of the second position. We again get a scalar weight that might be a little bit higher because maybe neural is very much connected to networks, so they need to be interacting. Then we compare it to R, much lower weight. Again, this is a scalar that we get out of this that is also normalized across time. And finally, we compare it to the word cool. And of course, we have a very high weight that is the output of this. So now we have for each time step, by comparing the query to the key, we have a weight that is just a scalar that we can then use to get a weighted sum of all our value vectors. So we just multiply the weight for each time step with its value vector to generate, and then sum across them to generate the output of our self-attention layer for the first position. Zooming out a bit, we can see that the network or layer function here weighs the different time steps differently and takes those as the input to generate its own output. And here, for example, the word neural is very much connected to the word networks and the word cool, but not that much to the word R. And this is applied in the same way in each time position, where in each time position we then would use a different word to generate the query vector and compare to all the other positions, and therefore we would also get a different weighing across time. But nevertheless, since we are sharing all the weights of these functions across time, we would have a very interconnected network that we would then call a transformer network because it transforms the entire sequence. And we can stack those transformer layers on top of each other to get a very good representation of an entire sequence, and then do some classification, for example, based on one position in this network. And we could also do something like language modeling, where we restrict the context of each time position only to its past. So we prevent, for example, the word networks at this position. The network functions could only look into the past but cannot get any context from the future in time. And therefore we can ensure that we, without cheating, generate the sequence one word at a time. We can also apply this to vision. Here we would transform an image into a sequence of small image patches that are then used as the input to our transformer network with some additional positional information that tells the network where in the image this patch is from. And then this transformer network can transform and process the entire image very efficiently and then generate an output, for example, a classification label from that. And this is very successful in the vision area and can lead to state-of-the-art performance, for example, on image classification. Finally, it is not that easy to train transformers because they need a lot of data, but if you have that data, you can actually scale them to an incredible size. Here, this is an example of NVIDIA where they scaled a language model to 1 trillion parameters. And this many parameters that handle a lot of data is a good way to achieve state-of-the-art performance on many tasks. So scaling up your model and your data leads to very good performance, but they do need a lot of data to perform that well. And this is because they don't have many restrictions, like for example, the local window that convolutional neural networks would look at is something that transformer networks need to pick up from the data and don't have built in. But that also makes them very flexible, so they can learn a lot of stuff if you give them a lot of data. Finally, wrapping things up for sequences, deep neural networks can be very successful for sequences. We have mainly seen that now for text data, but also for speech, signals, or time series data, they can be very successful and are easy to apply. Recurrent neural networks are what is traditionally used for sequential data, where they are designed to actually handle this context over time. Transformer networks are a more recent addition to all of this, where they actually do process the entire sequence with a context that is interconnected across time and lead to great performance.